Hi everybody, this is your video with sample free response questions on linear regression. So I've got 4 sample problems for you here. One of them is an investigative task, which is the last free response question that you'll see on the AP test. It's longer than the others typically, and tends to combine a lot more aspects of statistics together into one question. They also may have you extrapolate a little bit and try to expand and push your knowledge and understanding of statistics. So I wanted to do an example for you of an actual investigative task. So I found a good one that deals mostly with linear regression. All right, so let's go ahead and jump into it here. Okay, so this in this first question, I have a lovely scatter plot, which you can see on the right side of your screen, on the right side of the document. They also gave us the Minitab output for that. And then, as you can see, there's this point P up here in the top right corner that looks like it's heavily influencing the correlation, the slope, the y-intercept of this data set. So they also gave you a Minitab output without point P. Okay, so they removed point P from the data and generated this second Minitab output. So the question here is, does P exercise a large influence on the regression line? And the answer here, I'm hoping you can kind of see, is, well, yes, it does. If you remove P, then it looks like the correlation is going to go down, the R squared value is going to go down, and the slope may end up even being negative, right? Which you can see in the Minitab outputs, right? If you look and compare the y-intercepts, it was 8.1 and now is 11.1. Slope changes from 0.49 to 0.15, so definitely decreases. And then the biggest change is here in the R squared value, right? It drops to almost 0. So if you're answering this question, you need to, one, answer it and say, yes, point P exercises a large influence on the regression line. Okay, and then you have to talk about a couple of the changes that you see, right? So when P is removed from the data set, the slope of the least squares regression line changes from 0.4919 to 0.1500. The y-intercept increases from 8.107 to 11.123. And then the coefficient of determination, and that's R squared, drops significantly from 47.6% to 2.5%. Okay. So you have all of this information, and you would get this part essentially correct as long as you talk about at least 2 of them. That's what it says in the rubric for this one. So just identify as many changes as you can that you can easily talk about, right? And that would be your explanation part. Okay. All right. Then part B says that they looked back at the data and said point P actually was recorded incorrectly, and it actually should have been point Q. So now the point that we are looking at is down here in the bottom right corner. So what they want to know is, how is the least squares regression line going to change? So you need to talk about both the change in the slope and in the y-intercept. So the slope is the easiest part to identify, right? In the original, the slope looked more like this, and with point Q, the slope looks more like this, right? So definitely the slope is going to decrease, right? So the new regression line will have a negative slope rather than a positive slope. Okay, and then you also want to talk about the y-intercept. So because of the nature of the least squares regression line, the y-intercept when point P was in the data set is going to be much smaller than the y-intercept when point Q is in the data set. So you would say the y-intercept in the new least squares regression line will be, be much larger for the corrected data set, right? And that's it for that one. Okay, so again, the point of this problem mostly is for you to be able to talk about the importance or what influence points like point P and point Q can have on a data set, right? So the impact of outliers and influential points, as well as being able to read and interpret a Minitab output. All right, so give me a second to delete some stuff and clear my screen off, and then we're gonna look at the next question. All right, y'all. So here is the next free response question. So in this FRQ, we have a data set of height in inches and arm span in inches. And we're trying to figure out what the relationship is between those two variables. And I only have 12 data points here. So you have this first scatter plot, and they just want us to describe the relationship between arm span, and height. So remember, when you're describing the relationship between two variables in a scatter plot, you have to talk about strength, direction, and form. So I would say there is and then we're going to talk about strength. So I would say you could say strong, or I'm going to say moderately strong. So a moderately strong, okay, so that's strength. Direction is either positive or negative. So this is definitely positive. So moderately strong, positive. And then form is linear or nonlinear. So that looks linear to me. So I'm going to say linear relationship between, and then you put your x variable and your y variable. So between height and arm span, both in inches. Okay, and then it's a good idea to, you could leave it at that, but you could also add a short sentence at the end, just putting that sentence that you just wrote into more layman's terms, which is just that essentially taller students have longer arm spans. Okay, you would get all of the points that you needed just with this first sentence, though. Okay, all right, so let's look at part B. So I have two graphs here. The first graph shows the least squares regression line. Okay, and then the second graph shows the line y equals x. So this line, the least squares regression line, is the best line for predicting arm span if you know a person's height. But it's this one here, the y equals x graph, is going to help us with something called a classification of body types, which is what this part is about. So part B says that we can classify people into one of three body shapes: square, tall rectangle, or short rectangle. So a tall rectangle would be like someone that has a shorter arm span. So their arms are shorter, but then they're pretty tall, right? And then a short rectangle is exactly the opposite. So somebody that has longer arms, but maybe is a little bit shorter. Okay, so if we look at the least squares regression line, this line is good for prediction, but it's not great for classifying these body types, right? Because it doesn't give us a clear indication of just looking at the data points, which person has a longer arm span than their height, which person has a greater arm span than their height, uh, and a person who has an arm span that's equal to their height. You would have to look at each individual data point and analyze it from there, right? But this line, y equals x, along the line y equals x, remember that x is height and y is arm span. So along the line y equals x, we have people whose arm spans are equal to their heights, right? That's what this means, the y equals x, right? People above the line have a larger arm span than they do height, right? So their arm span is bigger. So they would be short rectangles above the line. And then below the line, we have our tall rectangles, people who are taller, right, or their arm span is less than their height. So part I here says which is helpful in classifying body shape and explain, right? So I kind of already talked you through this. So the line in graph 2 is helpful, okay? And then you have to explain. So what I would say, the way I would explain this is, for each student, this graph shows whether, I would say shows visually whether arm span is equal to height, right? So points on the line as line is y equals x, or arm span equals height, okay? So it'll show you whether arm span is equal to height, arm span is greater than height, points above the line, or arm span is less than height, which is points below the line. Okay. All right, then they want us to complete the table of classifications for these. So I'm going to use graph number 2 and see how many people fit in this square category, tall rectangle, and short rectangle. So for the square, there's three people that fall on the line. 1, 2, 3. So I would put 3 here. Okay, there's 3 people. Remember, frequency is just the fancy statistics word for count. Okay, tall rectangle is those that are below the line, right? Tall rectangle is below the line, so there's 4 tall rectangles, right? Height is greater than arm span, and then the remaining 5 are short rectangles that are above the line, okay? All right, and then part C says, using the best model for prediction, calculate predicted arm span. Okay, so even though this graph 2, is the best for classification, the least squares regression line is always the best line for prediction, always. Okay, so I'm going to use my least squares regression line equation. So they gave me a senior with a height of 61 inches. So I'm going to say y hat equals 11.74 plus 0.8247 times 61. Okay, and then plug all of that in, simplify, and I got 62.05 inches. All right, y'all, so that is it for this question. The next one is the investigative task. So give me a second again to clear my screen off, rearrange some things, and then I'll be back to look at this next FRQ. All right, folks, so let's take a look at this next FRQ, which, like I said, is a number 6, so it's an investigative task. So it has more parts and is having you combine things a little bit differently and maybe expand upon your knowledge of statistics using a data set that they give you. Okay, so in this data set, we're looking at the relationship between starting salary and the number of semesters that people take in an academic in academic programs in college. Okay, so that's what we're looking at. Right? So part A just says, does the scatter plot support the newspaper report about the number of semesters and starting salary? So what the newspaper reports is that that more semesters are needed to complete the academic program, then the greater your starting salary. Okay, um, so so I would say, just based on this, that just this graph, that yes, I agree. Right? If you look at the more number of semesters that people took, in general, the higher their starting salary was. So the relationship here is a positive association or a positive relationship, and that's essentially what the newspaper is describing. So I would say yes, the scatter plot supports the newspaper report uh, about the relationship between number of semesters and starting salary. Okay. The scatter plot shows a positive association between these two variables, right? I.e., the students who took more semesters had a higher starting salary on average. Okay. All right. So part B gives us the Minitab output for this data, right? And they want us to identify the slope and interpret slope in context. So remember, when you're looking at Minitab outputs, what you need to look at for now, and really for almost every problem, is this first column right here, the coefficient column. And remember that your y-intercept is the first value, and then your slope is this second value. So my slope is this number, the 1.15. Okay, so I would say the slope is 1.1594, and then your interpretation is for every, oh, actually, no, I'm going to write it a different way. Sorry, I want to make sure that I write it the same way that I've taught you guys with the script. So you put your y variable, which is starting salary. So starting salary is predicted to, and then you say increase or decrease. So this is increase, to increase by 1.1594. And then you have to put your unit, which is 1,000 euros. 1,000 euros. And then you could put the phrase on average if you want, on average. When the number of semesters needed to complete an academic program increases by 1, right? I.e., whenever you add an additional semester to the required course load. Okay, you didn't necessarily need um, you don't necessarily need this IE. I'm just writing it for you here so that you can see like what that would be in layman's terms, right? So you're adding an additional semester. It looks like on average your starting salary will increase by 1.1594 thousand euros. Okay. All right. So here we have a different scatter plot. It's the same scatter plot, but they broke it apart a little bit and showed you the relationships between majors. So all of the business majors are here in these open circles. The physics majors are the closed circles, and then the chemistry majors are the little X's. Okay. So what you can see is that even though the trend overall is positive, if you isolate within the individual majors, the actual trend is negative, right? So part C says, based on this, describe the association between starting salary and the number of semesters for business majors. So my business majors, are these, right? So again, we're still describing a relationship. So that's still strength, direction, and form. So you would say for business majors, there is a strong, I would say strong, negative, there is a strong, negative, linear relationship, or you could say association, between the number of semesters and starting salary. Okay, in layman's terms, that means business majors who need a greater number of semesters to complete an academic program tend to have lower starting salaries, which I think intuitively makes sense to us, right? Because if it takes you a lot longer to complete your degree, when you go out to try to get a job, right, you may not be able to get as high of a salary job because it took you longer to finish your degree. Right? Okay, part D says, based on the people in the sample, compare the median starting salaries for the three majors. So this is a little bit tricky, partially because we don't usually talk about median when it comes to scatter plots, right? That's not usually something that we look at. But remember that what scatter plots really are is it's like two dot plots plotted against each other, like on an X and Y axis, right? So I could take all of my business majors and have those dots fall so that they would be down here, right? And then you'd be able to pick out a median, right? Same thing for the physics majors and the chemistry majors. So what we have to look at is median starting salary. So essentially what we're doing is we're looking at the Y values and almost collapsing all of the data this way to see where the medians are. So you're looking for the middle, the vertical middle in each group. So I would say the vertical middle in the chemistry group is about like right here. So somewhere around 55,000 euros. The middle for the physics majors is probably about there, which is maybe like 48,000. And then for the business majors, it looks like the middle's about right here, which looks like about 37 or 38. So I'm going to say $38,000. Okay, so we just need to now compare these. So you would say business majors have the lowest median starting salary at around 38,000 euros. They are followed by physics majors, sorry, let me go like this so this goes back, at around 48,000 euros. Chemistry majors have the largest median starting salary at 55,000 euros. Okay, so there's your comparison. All right, last part here, part E, says, based on this analysis, how could the newspaper report be modified? Right, so really what they need to do is they need to make a note to separate this by major, that certain majors, overall majors that take longer, you will have a higher starting salary, right? But if you take a long time to complete your degree within that major, your starting salary actually is going to be lower, right? So what the newspaper needs to do is they need to account for major. So the newspaper report should account for major, right? And then you just have to explain essentially what I just did, which is that overall, majors that take longer to complete, like chemistry, have a higher starting salary those that take less time, like business, tend to have lower starting salaries. However, within each major, students that take a greater number of semesters tend to have lower starting salaries compared to their peers in the same major. Okay, so the reason that this is a little bit more complicated is because they're asking you to definitely expand upon your knowledge a little bit and do things that you may not be used to doing. For example, comparing a median, but for a scatter plot, right? So the beginning is something a little bit more like what you're used to seeing, right? Like interpreting slope and talking about association, right? But then when you get down to parts D and E, it's a little bit more out of the box and you have to think a little bit more out of the box. All right, so one more time, let me pause this really quickly, clear my screen off, and then we're going to do one more FRQ. So I'll see you back here in just a moment. All right, folks, so let's take a look at this last free response question. So in this one, we're talking about data for gray wolves, and the two variables that we're comparing are length in meters of the wolves and weight in kilograms. Okay, and then they gave us a description of this relationship. They called it positive, strong, and linear. Okay, so for part A, they're asking to explain what each of these words means. So what does positive mean in this context? What does linear and what does strong mean in this context? Okay, so positive means that when one variable increases, right, or is larger, the other variable tends to also be larger, right? So that's what positive means. And then we just have to take that and put it in context, right? So a positive relationship, oops, we turn that underline off. So that means that wolves with a longer length also tend to have higher weights. Okay, right? Right. So essentially what you're doing for all three of these parts is you're just taking the definition of each of these terms right? Or the general idea of these terms and then putting them in the context of this problem. So linear means that when the x value, right, or the x variable increases by 1, then the y variable will increase by a constant rate. Okay, that's what linear means, right? Right, and that constant rate is slope. So a linear relationship means that as length increases by 1 meter, weight tends to change by a constant amount on average. Okay, notice that I said that the weight tends to change rather than saying the weight tends to increase, because at this point in the problem, we don't know whether the weight is increasing or decreasing. Well, I mean, we do know it's positive, but if you're talking about a linear relationship, you don't have to be as specific as the slope, like going up or down, right? For linear, if you're just interpreting that word, right, it just means that the y variable tends to change at a constant rate or by a constant amount every time the x variable increases by 1. Okay, and then strong just means that the relationship falls close to a aligned pattern. Okay, so a strong relationship means that the data points fall close to a line. You can say or curve, because technically that's also true. But here this is linear, so you could just say line and that would be okay. All right, so let's take a look at part B. Once we get to part B, they give us a an equation for the least squares regression line. So they want us to interpret the meaning of the slope in context. So remember, your script is, you say the y variable, whatever it is predicted to then either increase or decrease by, and then you put what the slope is, and then you can put the phrase on average in here. Still, that would be awesome. So the y variable is predicted to increase or decrease by this amount when the x variable increases by 1, and then put the unit of your x variable. Okay, so for this problem, the y variable is weight. Okay, so weight of wolves in kilograms is predicted to increase, right? Because if you look, my slope is right here, 35.02. Okay, so is predicted to increase by 35.02 kilograms on average when the wolf length increases by 1 meter. Okay. All right. Then my last part here says one wolf in the pack has a length of 1.4 meters and a residual of negative 9.67. And they want to know what the actual weight of the wolf is. Okay, so remember that the residual equals the actual weight minus the predicted weight. Okay, so if I plug that information in, right, I know the residual and then I know the length, but I don't know the weight. So what we have to do is plug the weight, or not the weight, apologies, the length that we're given into the least squares regression line in order to get this, the predicted weight. Okay, so that's what I'm going to do. So I have y hat equals negative 16.46 plus 35.02, and then I'm going to multiply that by x, which is 1.4. So y hat, which is the predicted weight, if you plug all of that into a calculator and simplify it, you get 32.568 kilograms. Okay, so that is my predicted weight, right? And what we are looking for is this, the actual weight. So now I have enough information that I can plug, oops, hold on. I'm going to have to type it here. Actually, I may have to switch over to writing because it's messing up my writing here. So now I know my residual is negative 9.67 equals my actual weight, x, because that's what I don't know, minus 32.568. Okay, so all I'm going to do is add 32.568 to both sides. Okay, and then what I end up with is x equals, that equal sign is terrible. Let's try that again. X equals 22.898 kilograms. Okay, and that is my final answer. All right, you all. So I hope that this was helpful and informative for you in how to go about answering linear regression free response questions. All right, so I will see you in the next video, in the next unit. All right, bye, everybody.